Well, hello. I hope you are enjoying your snow day. I certainly hope all of you are staying warm and safe. Because of the shortness of time, I wanted to talk a little bit about the special case of finding volumes. You remember that yesterday in class we said that we could calculate the volumes of solids by considering the areas of cross-sections, and that the volume would be equal to the integral of the area dx if the cross sections are perpendicular to the x-axis. Or the volume is equal to the integral of area dy if the cross sections are perpendicular to the y-axis. What we want to consider now is a very special case of solids that have a particular cross-section called solids of revolution. A solid of revolution is a solid that is created when you take a region in the xy plane and revolve it about a horizontal or vertical line. For example, consider the curve y equals the square root of x, and the vertical line x equals 4, and the horizontal line y equals 0, which is the x-axis. These curves define a region here. And if you can imagine taking this region and bringing it around the x-axis, like so, then what we have formed now is a solid of revolution. It's sort of bowl-shaped or bullet-shaped here. In fact, I can get the computer to illustrate this better than I can. I have exactly that curve here in f of x, and I can let this region be defined as the region from x equals 0 to x equals 4. And if I now take this region and tell the computer to rotate around the x-axis right here, then it will give me a lovely solid. Now it changes the axes a little bit, so let's get it back to more or less where it was before. There we go. And now let's take a look and see how that solid is created when we take the region and we now begin to slowly revolve it about the x-axis. You can see how that region, that solid is being created. That is a solid of revolution. And you can imagine that if we take these solids of revolution and we cut them perpendicular to the axis of revolution, then what we get are a lot of cross-sections that are circular disks. And so our plan for finding the volumes of solids of revolution is to add up a bunch of circular disks. Let's take our cross-section here, which has a thickness of dx, and let's examine it. What we have is a circular disk with a radius, and let's call this radius capital R for radius. And because my circular disk is essentially a cylinder, circular prism, essentially, then the area of that cylinder is going to be pi r squared, and therefore the volume of my representative disk right here is going to be area times dx, or pi r squared times dx. And therefore the total volume of this solid, the entire thing, is going to be found by adding up all of those disks. The volume is going to be the integral from first to last of pi r squared dx. And usually we bring that constant pi to the outside. And sometimes you'll see me emphasize the fact that the radius is a function of the variable x. Well, how do we find that radius? Because you can see that if we can simply identify the radius of our representative element, then we're good to go. So how do we find that radius? That radius is going to be the distance from the outside of my circular disk to the axis of revolution. Going back up to our original thing right here, it's going to be the distance from the outside curve to the axis of revolution. So R is the distance from curve to axis of revolution. And in our particular problem, the axis of revolution was the axis y equals 0. And so the distance then is found by subtraction, and we can say that radius as a function of x is equal to the distance from the curve to the axis. Our slogan here is going to be curve minus axis. So putting all of this together then, we can say that the volume of the solid that we created is going to be equal to the integral from 0 to 4 of pi r squared dx, and the radius of my disks at each point x are going to be equal to root x. So we have the integral from 0 to 4 of root x squared, which is just x. Integrating, I get pi x squared over 2 from 0 to 4, which is equal to 16 over 2 times pi, which is 8 pi. Now, what is the meaning of saying that my radius is the square root of x? What I'm saying by that is this. Over here, when x is equal to 0, this point, 0, essentially creates a disk of no radius. Then when x is equal to 1 and y is equal to 1, now I have a radius of 1. And out here when x is equal to 4 and y is 2, my radius is the square root of 4, which is 2. So you can see that I've got disks of all sorts of different radii that are being stacked on top of one another to form this entire solid. Now, for the technical details, when I cover my solid with these disks really are an approximation. And what I'm doing is taking a look at the limit as the width of those disks goes to 0. So this is the typical way in which a problem will present. Here's a typical example. Let R be the region defined y equals the square root of sine x and the y-axis, excuse me, the x-axis for x's between 0 and pi. Find the volume of the solid generated when the region R is revolved about the x-axis. So what we have is a particular region, and we have an axis of revolution. These are really the two things that we want to look for here. And we want a sketch of our region. And so we sketch, what in the world does y equals square root of sine x look like? Well, I don't know. But I do know that when x is equal to 0, y will be 0. And when x is equal to pi, y will be 0 again. And when x is equal to pi over 2, y is going to be 1, and so it's going to be positive in between. And so it looks, I don't know, something like a sine curve. It's going to be a little more flattened than a sine curve. And so this is our region from here to here. Now we're going to take our region and we're going to revolve it about the x-axis. So this is our axis of revolution. And that causes this entire region to swing out and around so that it forms disks as it goes. And my disks are going to look like this. And so if I pull one of these disks out to examine it, that disk is going to have a thickness of dx, and it's going to have a radius of curve minus axis. So the radius is equal to curve minus the axis, just like so. And therefore, the volume of the solid that is generated will be the integral of pi r squared, that's the area of our disk, times dx, which is the thickness of our disk, taken from the first x out to the last x, from 0 to pi. Well, we've got our radius, we've got our integral formula, it's time to substitute and evaluate. So, and the square root of sine x squared is sine x. And we've actually done this integral a couple of times. We know exactly how it goes. We're going to get negative cosine x from 0 to pi, which is equal to the opposite of negative 1, cosine of pi, minus negative cosine of 0, for a total of 2 pi. So when we consider how we found the volume of this solid of revolution, it really came down to identifying the radius of my representative disk right here. And that radius was given by curve minus axis. Let's do one more showing how this might work if our axis of revolution is vertical, such as the y-axis. Let S be the region defined by y equals x squared and y equals 4. Find the volume of the solid generated by revolving S about the y-axis. We're going to start with a sketch of our region. And here's our region S with intersection points that are well known. Here's the curve y equals x squared, and here's the curve y equals 4. And now we're going to take this region and we're going to revolve it about the y-axis. So here's our axis of revolution. And that means this entire region is now going to be taken around the y-axis. And when we do, we form kind of a bowl shape like this. And if we take a cross-section that is perpendicular to the axis of revolution and pull it out, then what we have now is a disk whose height is dy and whose radius is going to be curve minus axis. But my curve now needs to be defined in terms of x as a function of y. So let's take our y equals x squared and rewrite that as x equals the square root of y over here. You could also use x equals negative root y over here, but that is just introduces extra negative signs that we don't really need. So we have x equals root y as the equation for our curve, and therefore the radius as a function of y is going to be equal to curve minus axis. Notice that I have to use y as my variable because dy is the height of my disk. because my axis of revolution was vertical. So vertical axes of revolution, like so, are going to lead to integrals in terms of y. Whereas horizontal axes of revolution are going to lead to integrals in terms of x. So now I've got my radius, and I'm ready to go, because the volume is equal to the integral of area, which is pi r squared, for this, times dy. And I'm going to be integrating from the first y value, 0, up to the last y value, which is 4. And interestingly, you can see that the integral that I have is exactly the same as the integral for our introductory example, except that it is in terms of the variable y instead of the variable x. Compare these two. Pi integral 0 to 4 root x squared dx, and now pi integral 0 to 4 root y squared dy. Exact same number, which is 8 pi. And when you look at the regions, you realize, oh yes, I can see why that's the case, because all I did was take my solid from the introductory example and put it on a different axis. Let's do one more example so that you can see some of the interesting things that can arise here. Let's go back to the region. Defined by y equals root x and x equals 4 and y equals 0, which is the x-axis. This region was the region from our introductory example, and it looks just like this. We have an intersection point here of 4, 2, like that. And now, here's my region R. Let's find the volume of the solid generated when R is revolved about the line x equals 4. Now, the axis of revolution that we're talking about, x equals 4, is a vertical axis, and so we expect that we're going to integrate in terms of y. And if you take a look at the solid that we have, when we revolve this entire region about the line x equals 4, what we're going to end up with is a solid that looks kind of like a dome, right? My artwork is bad here. Let me see if I can do this a little better. Imagine bringing this region around, and what you're going to end up with is a dome kind of a shape, like so. And so if we take a representative disk and we bring it out and examine it like this, then you can see that we have the axis of revolution going straight through like this. And the radius that we have is now going to be the distance from the curve to the axis. So again, we have axis minus curve, except this time, because the axis is to the right, we're actually going to do axis minus curve instead of curve minus axis. So that the radius as a function of y is going to be equal to, we need for x to be written in terms of y. So the radius as a function of y is going to be equal to the axis minus the curve. Notice that I turned my slogan around because my axis was to the right of the original curve over here. But here is a nice little secret, and that is that if you are a little unsure the squaring process will eliminate any negative sign errors. So I can always do curve minus axis, even if I end up with negative values because. So the volume is going to be equal to integral of pi r squared dy. And that's going to be taken from the very first y, which is y equals 0, right here, up to the very last y, which is y equals 2, right here. And the radius is 4 minus y squared. Now, don't forget that we're squaring the radius. So the volume is going to be pi times the integral from 0 to 2 of 4 minus y squared again. This is r squared dy. And this is just a matter of multiplying out the square so that I get the integral of 16 minus 8y squared plus y to the 4th dy, simply multiplying the square out. Wow, that was bad. Let me try again. So we go for the antiderivative, and we get 16y minus 8/3 y cubed plus 1/5 of y to the 5th from 0 to 2, which is pi times 32 minus 64/3 plus 32/5. If we are really ambitious, and since we're sitting at home on a snow day and we've got very little else to do, we can afford to be a little bit ambitious. We can go ahead and combine with common denominators, but it's a pain. So we have 15ths as our common denominator. And this is going to be 3 times 32 is 96. And this is going to be 5 times 64 is 320. And this is going to be 32 times 15. Which is 480. So that when the dust settles, we get 160 plus 96 is 256 over 15. You can imagine that I only do those kinds of computations when I really feel like I need a single one. So to review everything that we've done here, solids of revolution always create solids that have circular cross-sections. Because they have circular cross-sections, therefore, the area of my circular cross-section is always going to be pi r squared times thickness. If my cross-section is taken about the horizontal axis, like so, then my radius is going to be a function of x, and therefore the volume will be equal to pi times the integral of r of x squared dx, taken from first to last. If, on the other hand, my axis of revolution is vertical, then the width of my cross-section is going to be y, and my radius is going to be a function of y, so that the volume will be equal to pi times the integral from first to last of r of y squared dy, just like this. So in many ways, the solids of revolution, I think, are a little bit easier to work with than the solids with constant cross-sections, because the area formula is always known. And all I have to do is to identify that radius. And how do we identify the radius? By using our slope curve minus axis. This is the only thing that is going to cause a little bit of trouble, and that is if you forget the slogan, curve minus axis, you will be tempted to try to do something like top curve minus bottom curve or something like that. Just remember that the radius is always the distance to your axis of revolution. And if you remember that, you'll remember the slogan. And if you remember the slogan,